Existence, uniqueness, and the potential functions. This section collects existence and uniqueness results about equilibrium flows in non-atomic and atomic selfish routing games. We also introduce the potential function method, a fundamental proof technique. Non-atomic selfish routing, existence, and uniqueness. Our next goal is to show that in non-atomic selfish routing games, equilibrium flows always exist and are essentially unique. By essentially unique, we mean that all equilibrium flows of a non-atomic instance have the same cost. In particular, the price of stability, section 17.1, and the price of anarchy coincide in every non-atomic instance. Formally, our aim is to prove the following theorem, theorem 18.8, existence and uniqueness of equilibrium flows. Let G, R, C tuple be a non-atomic instance. A. The instance GRC admits at least one equilibrium flow. B. If F and F wave are equilibrium flows for GRC, then C of FC is equals to C of FE flow for every HE. Part B of the theorem and definition 18.1 easily imply that two equilibrium flows of a non-atomic instance have equal cost. We prove theorem 18.8 with the potential function method. The idea of this method is to exhibit a real valued potential function defined on the outcomes of a game such that the equilibria of the game are precisely the outcomes that optimize the potential function. Potential functions are useful because they enable the application of the optimization techniques to the study of equilibria. When a game admits a potential function, there are typically consequences for the existence, uniqueness, and the inefficiency of equilibria. To motivate the potential functions corresponding to non-atomic selfish routing games, we present a characterization of optimal flows in such games. To state this characterization cleanly, we assume that for every HE of the given non-atomic instance, the function x times c of x is continuously differentiable and convex. Note that x times c of x is the contribution to the social cost function by traffic on the HE, and let C star of x equals to x times C of x to the first differentiate, which is equals to C of x plus x times CE prime of x denotes the marginal cost function for the HE. For example, if C of x denotes the cost function C of x equals to a times x to the p for some constant a and p which are greater than or equals to 0, then the corresponding marginal cost function is c star of x equals to p plus 1 times a times x to the p. And let cp star of f equals to sigma summing for all e in p, the path p, of the term c star of f denote the sum of the marginal costs of the edges in the path p with respect to the flow f. The characterization follows. Proposition 18.9. Characterization of optimal flows. Let G, R, C be a non-atomic instance such that for every HE, the function x times C of x is convex and continuously differentiable, that C star denotes the marginal cost function of the HE, then F star is an optimal flow for GRC if and only if for every commodity I which is in the set 1 to 3 until k, and every pair P wave which belongs to the set Pi of SITI paths with Fp star greater than 0, then Cp star of F star is less than or equals to Cp wave star of F star, and proposition 18.9 follows immediately from the first order conditions of a convex optimization problem with non-negativity constraints. We omit the details and focus instead on how the proposition leads to a potential function for equilibrium flows in non-atomic instances and on the implications of this potential function for the existence and uniqueness of equilibrium flows. Definition 18.1 and proposition 18.9 immediately imply that equilibrium flows and optimal flows are the same thing, just with respect to different sets of cost functions. Corollary 18.10 Equilibrium of equilibrium, equivalence of equilibrium, and optimal flows. Let a GRC be a non-atomic instance such that for every HE, the function x times CE of x is convex and continuously differentiable. Let C star denote the marginal cost function of the HE, then F star is an optimal flow for GRC if and only if it is an equilibrium flow for GRC star. And for instance, in P-Gauss example 17.1, the marginal cost function of the two edges are C star of x equals to 1 and C star of x equals to 2x. The equilibrium flow with respect to the marginal cost functions splits the traffic equally between the two links, equalizing their marginal cost at 1. By corollary, 18.10 This flows is optimal in the original network. In the nonlinear variant of P-Gauss example 18.3, the marginal cost functions are C star of x equals to 1 and C star of x equals to p plus 1 times x to the p. The optimal flow therefore routes p plus 1 to the minus 1 over p units of traffic on the second link and the rest on the first, in a Bryce paradox with the zero cost edge added. Example 18.4 and figure 18.2b, routing half of the traffic on each of the paths S to V to T and S to W to T equalizes the marginal costs of all three paths at 2 and therefore provides an optimal flow. To construct a potential function for equilibrium flows, we need to invert corollary 18.10. Of what function do equilibrium flows arise as the global minima? The answer is simple. To recover definition 18.1 as an optimality condition, we seek a function he of x for each he, applying the previous rule of x times c of x, such that xe prime of x is equals to c of x, and setting he of x equals to the integration integrate from 0 to x of the term c of y dy for each he, thus yields the desired potential function. And moreover, since CE is continuous and non-decreasing for every he, every function he is both continuously differentiable and convex. And precisely co phi of f is equals to sigma, summing for he in the edge set E, capital E, of the term. Integration integrates from 0 to fe of the term c of x dx. So it's a sigma of the integration and the potential function of a non-atomic instance GRC invoking proposition 18.9 with each function x times c of x replaced by he of x equals to integration again from 0 to x of the term c of y times dy yields the same condition as in definition 18.1. We have therefore characterized the equilibrium flows as the global minimizers of the potential function phi. Proposition 18.11 Potential function for equilibrium flows. Let GRC be a non-atomic instance. A flow feasible for GRC is an equilibrium flow if and only if it is a global minima of the corresponding potential function phi given in 18.3. Theorem 18.8 now follows from proposition 18.11 and the routine calculus. Proof of theorem 18.8. We first note that, by definition, the set of feasible flows of GRC can be identified with a compact, i.e. closed and bounded, subset of absolute values of p-dimensional Euclidean space. Since edge-cost functions are continuous, the potential function is a continuous function on this set by Weierstrass's theorem from elementary mathematical analysis. The potential function phi achieves a minimum value on the set. By proposition 18.11, every point at which phi attains its minima corresponds to an equilibrium flow of GRC. For part B, recall that each cost function is non-decreasing, and hence each summand on the right-hand side of 18.3 is convex. Hence, the potential function phi is a convex function. Now suppose that f and f wave are equilibrium flows for GRC. By proposition 18.11, both f and f wave minimize the potential function phi. We consider all convex combinations of f and f wave, that is, all vectors of the form lambda times f plus 1 minus lambda times f wave for all the lambda which is in the closed interval between 0 and 1. All of these vectors are feasible flows. Since phi is a convex function, a chord between 2 points on its graph cannot pass below its graph. In algebraic terms, we have phi of lambda f plus 1 minus lambda times f wave, which is less than or equals to lambda times phi of f plus 1 minus lambda times phi of f wave. And for every lambda which is in the closed interval between 0 and 1, since both f and f wave are global minima of phi, the inequality 18.4 must hold with equality for all of their convex combinations, since every summand of phi is convex. This can occur only if every summand, the integrate from 0 to x of the term c of y dy, is linear between the values fe and the fe wave. In turn, this implies that every cost function c is constant between fe and fe wave. Atomic selfish routing existence. We now consider equilibrium flows in atomic instances. The AAE example 18.6, suggests that no interesting uniqueness results are possible in such instances, so we focus instead on the existence of equilibrium flows. Similarly, example 18.7 demonstrates that a general atomic instance need not admit an equilibrium flow. There are two approaches to circumventing this counterexample. The first, taken in this section, is to apply additional restriction on atomic instance so that equilibrium flows are guaranteed to exist. The second approach, discussed in remark 18.26, is to relax the equilibrium concept so that an equilibrium exists in every atomic instance. The key result in this section is the following theorem, which establishes the existence of equilibrium flows in atomic instances in which all players control the same amount of traffic. Theorem 18.12. Equilibrium flows in unweighted atomic instance. Let GRC be an atomic instance in which every traffic amount Ri is equal to a common positive value R. Then GRC admits at least one equilibrium flow. Proof: we obtained theorem 18.12 by discretizing the potential function 18.3 for non-atomic instances, and the proof of theorem 18.8a. Assume for simplicity that R is equals to 1, set VA of F is equals to doubling summation, summing for HE in the H set E, and also summing for all I indexed from 1 to FE over the term C of I. for every feasible flow f. And note that phi a is the same as the previously potential function phi for non-atomic instances, except that the integral integrate from 0 to fe of the term c of x dx has been replaced by the summing sigma from index I from 1 to fe of the term c of I, and since the atomic instance GRC has a finite number of players, and each of these has a finite number of strategies, there are only a finite number of possible flows, and one of these, call it flow, is a global minima of the potential function phi a. We claim that f is an equilibrium flow for GRC. To prove it, assume for contradiction that in an f, the player I could strictly decrease its cost by deviating from the path P to the path P wave, yielding the new flow F wave. In other words, we assume that 0 is greater than the following: Cp wave of F wave minus Cp of F, which is equal to sigma summing for all E, which in the P wave slash P of the term C of Fe plus 1 minus, again, sigma summing for all E in P slash P wave, which are exclusive of the term C of Fe. And on the other hand, consider the impact of player I's deviation on the potential function phi a for edges in P wave slash P. The corresponding sum in 18.5 requires the extra term C of Fe plus 1. And for edges in P slash P wave, the corresponding sum sheds the term C of Fe, and for edges of P intersect P wave, the corresponding sum remains the same. Thus, phi a of f wave minus phi a of f is precisely the third expression of 18.6. Since this expression is negative, the potential function value of f wave is strictly less than that of f, which contradicts our choice of f. Now, remark 18.13. Proof of theorem 18.12 established a remarkable property of the potential function phi a. It tracks the change in cost experienced by a deviating player, and more formally, for every flow, every player, and every deviation by a player, the change in the player's cost is identical to the change in the potential function. This property has consequences beyond the existence result of theorem 18.12. For example, it implies that Basler response dynamics are guaranteed to converge to an equilibrium flow. See Chapter 19 for further details. Remark 18.14. The proof of theorem 18.12 did not use any assumptions about the edge cost functions. In particular, it is also valid when cost functions are not non-decreasing. This property will be crucial for some of the network design games studied in Chapter 19, which can be viewed as atomic selfish routing games with decreasing cost functions. The next theorem guarantees the existence of equilibrium flows under a different restriction, fi cost functions. Recall that a cost function c of x is fi if it has the form ae times x plus be. We always assume that ae and be, both of them are greater than or equal to 0. The theorem is as follows. Theorem 18.15. Equilibrium flows with fi cost functions. Let GRC be an atomic instance with fi cost functions. Then GRC admits at least one equilibrium flow. The proof of theorem 18.15 follows the same outline as that of theorem 18.12, and uses a variant of the potential function method. See exercise 18.4 for further details.